Okay, we're in section 84. Again, there'll be contents. It looks a little bit lengthy to me from 1460. Then the example started page 1473. So it looks like a lot of reading to do. And then exercises. My name is Ron Bannon. This is a draft version of my adaptation of Webster Wells's Advanced Course in Algebra that dates back to 1904. The PDF that you're looking at here is being made available to the Prison Mathematics Project participants only. However, I realize that other people may be watching this, particularly students and teachers, that might be interested in getting a copy of this document. It's not yet published. When it's published, though, certainly you'll gain access to it. If you're interested, you can inquire about when it's going to get published using this email address over here, and that's B as in boy, that's Bannon, B as in boy, the @ nnon.us. And again, if you email me and I'm not overwhelmed, I'll certainly put you down for someone that's interested in getting a copy of this at some point. All right, this is a tough section. And what I mean by that, they're doing things here that I would say nowadays are not discussed in algebra anymore. And that's convergency and divergency of a series. Just to remind you, the series, we're going to have a sequence. Let me put a sequence down for you, something like this over here. I'll write this down for you. A1, A2, this is a sequence. And it goes on forever, all right? A series would be to add those terms together. A1 plus A2 plus A3, which may seem very strange to you. This goes on forever. And what we're really interested in, does it converge to a number? That's what we're interested in. Does it converge? All right, so we know some series already, and I'm going to claim that, at least I think you know them already. We've gone through some of this stuff over here. This is the geometric one, and we know that converges for proper fractions only. In other words, the expression 1 over 1 minus x equals that infinite series only for certain values of x. And again, those certain values of x would have to be between -1 and 1 for that to work. All right? This one over here, it's a binomial expansion, believe it or not. And it also converges for certain numbers. And we'll talk about that. But the bottom line is what we're doing over here is you read through this section over here, and it's a dense read. There's no doubt about it. You might have a tough time with it. But again, as I always encourage students, read, and read some more. But the bottom line with mathematics, all the reading, you're going to have to get busy thinking about what you read and then trying it out on examples. Of course, let me scroll through this. It's a really long section. Again, I'm not asking you to read it as I scroll through it. I'm asking you to sit down and attentively read that at some point. All right? And of course, after you read that, wow, this doesn't stop, does it? Yeah, it does. Eventually we get to examples. All right? Now, what I do is I realize that what Wells does and the way I would teach it would be different. All right? So I give an overview. And the overview I'm giving over here is I give an overview of how to generate this one over here. And there's many ways to do it, by the way, what it looks like in sum notation. I talk about, formulas, and I give you a summary of this one over here. And there's nothing wrong with looking back over your notes, by the way, when you're doing problems. Like you might say, I can't remember. You look back over your notes. Then I give a summary of convergence. All right? And, I'm going to say that we would love for you to read through this. All right? And certainly when you're doing the homework, you might have to look back over it. All right? Convergence, divergence of a series. It's an infinite series, by the way. All right? Talking about nth partial sums, things like that. Again, we'll go through examples, but again, part of it is just reading. Oh, I also want to emphasize here, I graph for you, and I want to point out what I'm graphing over here. I'm graphing f of x equals 1 over 1 minus x, which I clearly see. I want to point out what I'm seeing. That's this curve over here. By the way, it's not the full picture of it. It's this picture over here. It's not the full picture of it, though. Certainly, 1 over x is asymptotic when x equals 1. There'd be an asymptote over here. But there'd also be a picture on this side as well. We're not doing that, though. The other thing I graph out is I graph out the 10th degree polynomial of an expansion of this. And what would that look like? And it might be shocking that you can actually graph it out. 1 over 1 minus x, a 10th degree approximation to that would be this over here, 1 plus x squared plus x cubed, yada, 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 all up to x10. And what's remarkable when you graph that out, you're going to notice you get this magenta color curve over here. And it looks like this over here. And what it really kind of fits the curve nicely between values. And what values are between -1 and 1. That's the only way it's going to fit. And by the way, when I say it fits, it really fits it. But this is just a 10th degree one. It's not going to be a perfect fit. If you notice over here, a 10th degree one's not fitting over here. But the more and more you take it out, like if you go to x11, it's going to get closest. If you go to x100, it gets even closer. X1,000,000 gets even closer. You get the idea. It's going to be closer and closer as we start expanding it out. All right? This one over here is an expansion of, it's a graph of this guy here. I'll get black ink out. Sorry about that. All right? And then what I did is also the 10th degree expansion of this. And let me point out what I mean by that. 1 plus x. And again, we're not asking to memorize. There's an expansion to this. Let me just go back in the notes and show you. The expansion's right over here. And we'll actually compute some of these for you. All right? So what would the k be? The k would be 1/2, and we would expand it out for you. And again, we'll go through that. All right? I'll go through that. And when you do that, what you notice is you're going to get a curve, and that curve's going to look like this over here. It'll look like a different color. It's going to fit really nicely, though. And someone says, where does it fit between? Looking at it, you're getting, I'm not going to say a perfect fit, but it doesn't look bad between this range over here. It doesn't look bad, all right? So I'm going to keep going. And there's all kinds of tests that we use. Again, it's not easy. He does talk through this stuff, though. These are for positive term series, by the way. Let me make sure I said that somewhere. Infinite series. Again, positive term series. I'll just say that now. And we got some pretty. Actually, you know what? This is. I'm sorry. Maybe I shouldn't have said that. That's not true. They could be any term series. What are they doing? They're basically saying, if this series and this series converge, we can start to do things with them like add and subtract them together, and do a constant multiple of them. And that's nice to know. All right, it's nice to know that. Geometric series. That's a series over here. Something you should be quite familiar with it. The R, and we've done that before. Proper fraction. What does it mean between plus or minus 1? All right. So I did the infinite one, got the sum of it. We know it's divergent when the R is greater than or equal to 1. The absolute value of it, by the way. P-series, again, he doesn't really address this specifically, but he does talk about it, but he doesn't call it a P-series. Right, you get this over here. Again, we're just saying that you should read this stuff over here and try to make sense out of it. And again, he does address it. Right, he just doesn't call it a P-series. Divergent test, I'll put a little star next to this guy over here. Although not useful, it's really easy to do. And really what they're saying is that if you have a series, and this series over here would be A1 plus A2 plus A3, yada, 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 and you get AN over here, yada, yada, yada. What they're saying is just look at the limit of the terms. And they're saying if the limit of the terms, right? So it says if the series is convergent, they say the nth term as n goes to infinity must be 0, the limit of it. All right? Now, I don't want to get confused by that, but there's actually series, by the way, they're saying this series converges. They're saying it right over here. They are not saying that that if the limit as n goes to infinity of an is 0, the series converges. They're just saying it's a one-way street. It's a one-way street. All right? But I will say this, though. If the nth term, the limit, as n goes to infinity, of the nth term is not 0, in other words, it oscillates, or it's some other number, or infinity, the series is not going to converge. All right? And that's often confusing to students. Let's keep going. I got a comparison test over here. Comparisons test is nice if you have something to compare it with. And I'm going to say the things, this is for positive term, by the way. A good place to start with a comparison, by the way, is knowing a series or two. So I'm going to say a really good series to know would be the geometric series. This guy over here. This is a really good series to know, if you know that series. The other series would be the P series. Let me just mark them down for you over here. So I'm going to put a little star next to this one over here. This is really important to know, this one over here. Right? And the P series is really important to know. All right? Again, the geometric series for comparison purposes is really nice to know. And it's really a foundation of series analysis, in my opinion. So let me just go back over here. So this is really important. I'm going to have to star that for you. And this is really important. I'll star that for you. So what does it say over here? Again, the P series, I'm looking at it. If I write that down, I'll write it down for you. This is going to be what? 1 to the minus P plus 2 to the minus P plus 3 to the minus P, yada, yada, yada. You can do that forever. We don't want to do it forever. Where they're saying it only converges if the P is greater than 1, but it's divergent otherwise. And that's really nice to know. All right? Now this test over here, again, you want to think about that. Comparison test. Again, what we're talking about, the two big series for comparison purposes are going to be the geometric and the P series. All right? They're really important. Again, Wells does not use the term P series. P series now is typical, right? Very typical. And again, as we go through problem set, we'll talk about it. All right? Comparison. It's nice if we can do a comparison. What are you doing? You're basically comparing series, right? They're for positive term series. And again, we'll go through the examples and we'll talk about that. I prefer the limit comparison test, by the way. Not always, by the way, but I do like it because it makes it a lot easier. I don't have to do an inequality. And that's the problem with the comparison test. Inequalities are involved, and they can be quite difficult to solve. But a limit comparison is nice, really is. And there's subtleties, and again, the subtleties are not really addressed in this text, but I do write the subtleties down for you in the summary. We'd like you to read it. Okay, next up is alternating series test. What's an alternating series? A series that bounces back and forth between plus, minus, plus, minus, plus, minus. And then, you do two things. You look for this, you look for this. If that's the case, the series converges. All right? Ratio test. Wow, this one's really important. All right? It reminds me of a geometric comparison. And it really is. It really boils down to that. All right? So we're looking at, if you remember the geometric, you're looking at successive terms, and you want to make sure their ratio, remember the common ratio for the geometric, less than 1. So that's all that really is doing over here. It's saying like this is geometric, and it would be divergent for this over here, but there is a problem. If it equals 1, you cannot draw any firm conclusion from it. All right? So let's take a look, and as I do these things over here, I got to claim you. I'm not asking you to memorize. I know a lot of teachers do, but I'm not asking you to memorize. What I'm asking you to do is you have to go back on the notes and say, I wonder what this is. They want me to verify this. And I'm going to say, looking at that, you say, I don't know how to verify it. Well, it has to have something to do with the notes. And I'm going to say this is a binomial or a general binomial expansion. Now, what's their question? They want me to verify the first 4 terms. Now, let's say you can't remember the binomial expansion. What you need to do, you need to go back in the notes, and this is one of the reasons we type things up for you. You could actually look at it, and it's right here. I got to be honest with you, it's got a nice pattern to it, right? 1, and then K minus 1, K minus 1, K minus 2, 3 factorial, 2 factorial. Believe it or not, this would be 1 factorial. I get a Z factorial over there. I'm looking at the powers, 3, 2, 1, none. I'm saying it's got a really nice pattern to it, all right? And what are we doing? We're doing 1 plus x to the k. And k can be any real number. Let's go back over here. I'm going to write this down for you. And what do you get? You get, I'll write down each term, by the way. You get 1. The next term would be 1/2. That's what the k is, times x. Let's do the next term. It's not that bad to do. It's going to be 1/2, 1 minus 1/2 over 2 factorial x squared. I can write the next term down pretty easily. 1/2, and it really never stopped, by the way. 1 minus 1/2, and then it's going to be 1, I'm sorry, not 1, I'm daydreaming here. It's going to be 2 minus 1/2, right? And now it's going to be 3 factorial x cubed, all right? Now, what do they want to verify? The first 4 terms. Now, certainly you can go on. This certainly goes on. There's 1, 2, 3, 4. They're just asking me to verify the first 4. But if you want, you can go on as long as you like. Let's write this down. Well, first term is 1. That's verified. Next term is 1/2 x. That's certainly verified. So we verified the first, verified the second. Now let's do that third term in. What do you get there? This is 1/2. 1 minus 1/2 is minus 1/2. And we're dividing by 2 factorial. I'll write that down. 2 factorial is 2, x squared. And we'll do that later. What's this one going to be? 1/2 minus 1/2. And then what do you get? Well, 2 minus 1/2 is going to be what? 3/2, right? You know what? I made a mistake. And I really apologize for that. Man, I'm writing down the right things, but I put the wrong thing over here. And I got to put the right thing down. By the way, I want to point out what I did. Not thinking when I'm speaking. I want to go back over here. And I want to tell you it's k minus 1. I wrote something different. But yeah, it's easy for me to correct. And it's important that I correct what I write down. Right now, I did write the right thing down, minus 1/2, but what's above it is incorrect. That's what's wrong. Now, someone says, how do you know you got it wrong? I was looking at actually the arithmetic, and I realized that this is all wrong up here. Because the arithmetic wasn't producing what I wanted to produce. All right, let me write that down for you. And I apologize for writing the wrong thing down for you. It's 1/2 minus 1, 1/2 minus 1, 1/2 minus 2. And I do that often sometimes. I'm not thinking, I'm just writing. But so when I write, I realize I made a mistake. So minus 1/2. And then 1/2 minus 2 is going to be minus 3/2. These have incredibly nice patterns, by the way. 3 factorial is just 6. And that would be x cubed. Now, I got to verify. And I'll point out what I mean by that. This is verified. This is verified. I got to do this guy in here. What do I get over here? Well, 1/2 times minus 1/2. I'll do this on the side for you. It's minus 1/4. And if you're dividing by 2, you get minus 1/8. And I'll write that down for you. So it's going to be 1 plus 1/2 x minus 1/8 x squared. I'm going to do the next one. What do you get? 1/2 minus 1/2. We'll do that later. Minus 3/2. And then I'm dividing by a 6, and I'll write this over here. And this doesn't look too bad to do, by the way. Well, what I get? Well, I definitely get a positive number. I would get 3 on top. And what do you get at the bottom? 2 times 2 is 4, times 2 is 8, and 8 times 6 is going to be 48. And that certainly reduces to 1/16. I'll write that down. So 1/16 x cubed. So let's go back over a verification. And I got the first 2. I know that much. Did I get this one as a verification? Yep, I got it. Did I get this one? Yes, I got it. All right? So again, they explain the use of the formula, and I actually write the work down for you. This one over here says, use the formula. Well, we know what the formula is. This is the formula here. Right? Use the formula to verify the 7th term. So I'm going to start counting in, right? So we got 1, 2, 3, 4, 5, 6. Oh, they got it down for me. So we're verifying this one over here. Now someone says, how would you do that? Well, I got to write it down. I'm using the formula. And it's not going to be easy, but I have to write it down. And I'm going to put this down for you. I know I have x to the 6, right? All right, I just want to kind of review with you. We got over here. This is 3 factorial. I think you have the idea. All right, and then what do you get up here? You get all these kind of factors. How many factors? 3 factors. How many factors? 2 factors. All right, so I'm going to try to do that. But I'm not going to pretend it's the right answer. I'm just going to write this down now. And I know the bottom is 6 factorial. And I got to put this top part down. And what's going to be, I'll write it down very carefully too, 1/2. And then what is going to be? 1/2 minus 1, right? Let me sharpen my pencil here. There are going to be 6 factors, by the way. And they're going to have a really nice pattern, by the way. Let's see. I got 1, 2, 3, 4. I got 2 more factors to go, right? So 1/2 minus 4 and 1/2 minus 5. Well, I'm going to have to write this down. And what do you get? You get 1/2 minus 1/2. They have a very nice pattern, by the way. The next one's going to be minus 3/2. The next one's going to be minus 5/2. The next one's going to be minus 6/2. Let me make sure I'm doing that right. Yeah, 6/2. I'm sorry, 7/2. Let's see if I did that right. Yeah, because the difference between 8 and 1 is 7, right? And then 9/2, minus 9/2. Again, I'm going to put the 6 factorial down for you. And 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. All right, I got some arithmetic to do. Before I do anything now, I want to get the sign of it. Right, so how would you do that? I'm going to look at it. There's a negative here, a negative here, negative here, negative here, and negative here. So I have, there's 5 factors that are negative. 1, 2, 3, 4, 5. So I know my answer is negative. I know that much. Now I'm going to kind of write this down, and I got to be really careful. I'm just going to do the bottoms, and I know I get 6, 5, 4, 3, 2, 1. I know I get that. But now I got a bunch of 2's too, don't I? How many you got? 1, 2, 3, 4, 5, 6. So I'm going to write down 2 to the 6th power. We'll do that later. All right, maybe that doesn't look like 2 to 6, but I'll write it better. Give me time to get the eraser out. So it's 2 to the 6th power. All right? Now remember, I already took care of the sign. I'm just going to put the numbers down now. I'm seeing 3, 5, 7, 9. Well, you know what? I got to do some reductions over here. And it's always a problem for me doing those reductions because I have to look around for things. And I'm seeing some things. For example, I'm seeing 3 goes into 3 once, and it goes into 6 twice. All right, that's done. And I'm seeing 3 goes into 9 3 times. Right? I did that. I'm seeing 5 cancels, right? So what am I left with on top? I'm left with minus 21 now. That was really simple. Now what are you left with on bottom? It's not easy, by the way, I'll tell you that. There's a 2, there's a 4, which is 2 more 2's, and then it's followed by, let's write all these down. So I got a 2, I have a 4, which is 2 squared. I have another 2, and I have 2 to the 6. Let's just count the 2's up. 1, 2, 3, 4, 10. 2 to the 10th power. I realize some students are looking and saying, could I use a calculator to do that? Of course you can, but I want to do it in my fingers, and I'm going to start counting it off. 2 times 2 is 4. I'm using my fingers, by the way. 8, 16, 32, 64, 128, 256, 512, 1024. So I'm going to say that's the numerical coefficient. But again, I'm trying to verify this, right? And I did the numerical part, and I got that verified, and I got this verified too. So we just verified it. Not my chicken scratch, but I did verify it. All the work is down there for you, including me, putting everything down neatly for you. Again, when I'm writing up an answer key, it looks like chicken scratch, and then I got to type it up, and that's what's in the blue area, what I typed up for my chicken scratch. All right, find the interval convergence for this thing over here. There are many ways to do it, by the way, and I'm going to probably claim, one of the easiest ways to do it is to just write down a partial sum. So I'm going to write a partial sum down, Sn, and the partial sum Sn would be 1 plus x squared plus, I would go up to xn. And then what I would do is, there's many ways to do it, but I'm just going to multiply both sides by x. And you get xsn. This is called the nth partial sum. You would get x plus x squared plus yada, 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 xn plus x to the n plus 1. What I do next, I subtract. And I would get Sn minus x Sn equals, well, kind of looking at that, if I subtract it, I notice a lot of things disappear, right? What do I mean by that? If you're subtracting, let me put out what I mean by that. These things disappear, this disappears, everything in the middle disappears, this disappears, and you're left with something. What are you left off with? 1 minus x to the n plus 1. I'm going to find out what Sn is now by factoring it out, and it would be 1 minus x equals 1 minus x to the n plus 1. What do you get on bottom? I'm sorry, I didn't mean to do that part. I'm jumping ahead. I'm going to divide both sides by Sn's coefficient, and you can get a really simple formula for the partial sum. This is true for any n. It may not be true for any x, but it's true for any n. This is an interesting concept, by the way. If you were to do the long division, you'd end up with this infinite expansion here. But now comes my problem. What happens if I let n get really large? Let me write this down for you. The limit as n gets really large of Sn. Well, I have to write that down. That's a limit as n gets really large. And what's Sn? 1 minus x to the n plus 1, 1 minus x. Well, I want to outline to you the only thing that I'm really worried about is this thing over here. And what I want that thing to do is shrink, to disappear. The only way that would disappear is if x is a proper fraction. And the way we write that down is we say that x must be a proper fraction for that to shrink to 0. So let me write that down for you. What does it mean? The x must be between minus 1 and 1. So I'm going to say that's the interval of convergence, all right? Now someone's going to say, I wonder if you can include the number 1, and you can't. And why is that? That would be a division by 0, all right? Be a division by 0. You could also, look at, by when I say that it's over here, it's division by 0. Let's try the minus 1. What would you get? Well, if you try and minus 1, you'd get 1/2 equals 1 minus 1 plus 1 minus 1 plus 1 minus 1. I know by just looking at these terms over here that any element in the listing things would never go to 0. So this couldn't converge any number. This is not working. So this is the interval of convergence. Again, I know looking at this thing, for one thing, it could never equal 1/2, but more importantly, just by the test for divergence, every single term is 1. I know it bounces around, by the way, has no sum, all right? This will all explain to you over here. All right, this is an infinite series problem, and they're wondering, does it converge? And by the way, I know this is really rough material, all right, really rough material. But what I'm going to do is I'm just going to rely upon the test that we've been given to see if we can do it. Now, for me to do that, I want to point out it might be a good idea to write these as summations. In other words, those terms, which I'm not really seeing it at this point, have to be fractions, right? What do I notice? The tops are always the number 1, but the bottom appears to be 2 raised to some power. So I'm going to say 2 to the, I'm going to use the letter I. Now, I know they're using something different than those. I'm going to say I equals 0 to infinity. Let me start writing the terms down. It's going to be 1 over 2 to the 0 plus 1 over 2 to the first power plus 1 over 2 squared. I'm just doing the counter. It's the I part. 1 over 2 cubed. What does this give me? 1 plus 1/2 plus 1 over 2 squared. Yada, yada, yada. So now I know the nth term of the problem. And what I mean by that, this goes on forever, by the way. The nth term, I'll write it over here, an, is of the form 1 over 2 to the n. How do I know that? I'm looking at this. All right? So writing the sum down, writing the nth term down. Then we're going to use, you could use test for divergence, but unfortunately, let me put the test for divergence down. I'll outline what we're doing over here. The test for divergence, generally speaking, really doesn't help me much, but you look at the limit as n goes to infinity of that term, the nth term, which is 1 over 2 to the n, and that equals 0. And the fact that it equals 0 doesn't really give me any information about it. other than the fact that it could be convergent, but it doesn't say it is. It just says it could be convergent. It doesn't say it's convergent, by the way. So that's not helping me out. And again, you'd have to read that test over and over again and hopefully try to think about it. All right, so I'm going to say that test for divergence was of no help to me. So what do? I start looking for a test that might be easy, and we're just kind of playing around. And the ratio test's not bad. All right, so what's the ratio test? We'll write it down for you. And again, if you can't remember, I want to point out, let me go back over this with you. The ratio test is right over here. I like the ratio test, by the way. It's a really nice test to be using. All right, so someone says, I don't like the ratio test. You can do other things, but I like the ratio test. All right, and it kind of reminds me of, like, I'm trying to relate it back to a geometric, which would be the most, fundamental problem to understand from these problems over here. So, the ratio test, I'll write it down for you. It's a limit problem. I'll write it down, limit, and n goes to infinity. The absolute value of a n plus 1, I'll do this later, over a n. And I want it to be less than 1 for it to be convergent, all right? But right now, my main concern is, can I get that ratio and take its absolute value and then do the limit? Well, I got to write it down for you. So I'm going to write it over here. This is my little chicken scratch on the side. And I want to see if I can do it. And what do you get? Well, let's take a look. You get 1 over 2 to the n plus 1 over 1 over 2 to the n. And I got to be honest, it looks pretty crazy to me. But one thing I know about it is it's all positive term. So the absolute value is going to be removed. So I'm going to left off with 1 over 2 to the n plus 1 divided by 1 over 2 to the n. I can simplify that, right? And what do you get? 2 to the n over 2 to the n plus 1. What does this reduce to? 1/2. All right, now what do I know about the limit? The limit is a half, right? So I'll write this over here. The limit, as n goes to infinity, of a n plus 1 over a n is actually equal to 1/2. Now 1/2 is clearly less than 1. All right, so what do I know about this thing? By the ratio test, the series convergent. That's good to know. All right, let's go to the next one, number 5. And again, I know this is tough material. What I would recommend, again, is, looking at it, and I'll write this down for you. I want to look at the sum, see what it is. First term kind of disturbs me, by the way. But I'm seeing something, and it looks really tough, though, doesn't it? But one thing I know about it, the top is always the number 1. It's the bottom that disturbs me. And I gotta write these things so I see the exponent, too. So 3, 2, 1, and then none. Right? I'll write that down. So I'm going to say it looks like n. And we're going to start with n equals 1 and go to infinity. And then I'm looking at the exponent. It looks like the exponent is always 1 less than n. So I'm going to say n minus 1. All right, let's just see if it works out. What's the first term going to be? 1. 1 to the 0. What's the next term going to be? 1. 2 to the 1. What's the next term going to be? 1. That would be 3 squared. Next term is going to be 1 over 4 cubed, yada, yada, yada. It appears to be working out just as advertised. We're getting exactly what they said. Let me just erase this over here. We're getting exactly what they said. What am I saying? It's 1 plus a half plus 1 over 3 squared, 1 over 4 cubed, so forth and so on. So again, I'm going to look at the nth term. I'll write this down for you. The nth term is this over here. And unfortunately, again, I'm stuck with this. If I look at the test for divergence, or divergence test, I'm looking at the limit as n goes to infinity of an, which is this thing over here. And I hope you realize, looking at that, the bottom is going to blow up, and 1 divided by an incredibly large number is 0. So what does it say to me? It really says very little to me. It just simply says the limit is 0, and it's saying, yeah, maybe it converges, but maybe it doesn't. They're not really coming up with any conclusion. There's no conclusion from that. All right, so what I'm going to do is, I'm going to try the, you might say, I'm going to try the ratio test, but I got to be honest with you. I think I just want to, play around with this and see if it looks like anything I've seen before. And we don't have many things to look at. We really don't. So I'm going to kind of look around for things that we know about. And I know very little at this point. I know I could, for comparison purposes, Maybe I could use the geometric series. Maybe I could use the p-series. P-series seems unlikely, and I'll tell you why. The p-series has to do with an exponent that's not changing, and this exponent keeps on changing, all right? So I'm going to say maybe geometric, all right? Maybe a geometric comparison might be a good idea. And if you're going to do that, what you're basically doing is you're comparing term by term, right? So it says, what numbers would you choose? And I need to pick a convergent number. I want to put out what I mean by this. The geometric looks like this over here. All right, so I'm going to pick an x. And by the way, remember, for it to be convergent, the x must be between 1, minus 1, and 1. So I got to pick a fraction. Now, they're all positive terms, so I would pick definitely a positive fraction. And I'm going to start with a really simple one. I'm going to start with a half. So I'm going to start with x equals a half. So what would that be? Well, if I start with a half, which is easy for me, you can start with a different fraction if you want. But I know it converges. So I want to do like a comparison term by term. So, the first term of this series over here, I'll write them down for you. It's 1 half, 1 over 3 squared. I think you get the idea. I'm just writing them down. And I could do this forever. I really could. 1 over, I wouldn't want to do it forever. But what's actually going to be 1 over 4 cubed. You get the idea? But now I want to look at the geometric comparison, and I want to see what I get. I would get 1. Well, I got to be honest with you. This is definitely less than or equal to that. I know that much. And what's the next one, the geometric? Well, that would just be 1 half. Well, that's true too. What's the next one going to be? Well, the next one's going to be 1 over 2 cubed, which is 1/8. This may require some thinking over here, but I'm kind of looking at it and hope you realize this really says 8 less than or equal to 9. That certainly makes sense to me. I'm going to say that's true too. Let me just get the eraser out, because I think it's a pretty easy inequality. But again, if you're struggling with fractions, nothing's easy. What's over here? This would be 1/16, right? Well, I'm just testing the waters out. I'm not saying this is the only way to go about that, but you would get 16 less than or equal. 4 cubed would be 64. This works out beautifully too. All right, so I'm getting a pattern. All right, but someone's wonder, is the pattern going to hold out? Well, I want to just march off. And when I do that march off, I'm going to do ... I want to make a general statement down. And what's that going to be? Well, I'm going to write it down as n plus 1 to the n. And I want to see if it's really less than what I'm saying it is for the half power. What would it be? I want to put out what this is. This is going to be 1 half to the 0. This is 1 half to the 1. This is 1 half squared. This is 1 half. Did I do that right? I think I might have made a mistake here. I made a mistake. I got to correct it. 4. And I made a mistake on this one too. I didn't see I made the mistake, but it's good that I looked at it, and I want to write that over again. That's an 1/8, and I got to convince you again that these are correct. Sorry about that. Made a mistake there. And this would be 1 over 2 cubed. All right? But they're all true. Right? They're all true. You quickly look at that to know they're true, I think, anyway. For example, this one over here would be 4 less than or equal to 9. And this one over here would be 8 less than or equal to 64. Clearly true. All right? Clearly true. All right. Now, certainly, I'm going to see if I got this pattern over here that I'm writing down. And let's take a look at that. Well, it looks like the exponent is, 1 less than the number, like 4, 3, 3, 2. This would be 2, 1, and then you get the idea. So I'll write this over here. This is going to be 1 half. To the n now. All right? Okay, I want to put what I'm talking about. We're looking at this pattern here. This is 1, that's 1. This is none, that's none. We got that. Now, I'm kind of looking at that, and the big question is it true? Is it true for all n? You know, it requires some thinking, and I'll be honest with you. The problem with thinking, you can think your way out of just about anything, and if you're not good at reasoning, you can convince yourself things that are simply not true. So I want to look at it. I kind of want to look at it and write down in a simpler way for me. But again, your mileage may vary. This would be 1, and this would be 2 to the n, and this would be 1 over n plus 1 to the n. All right? So I want to look at that, and I want to see if I can solve that inequality without looking at my past, by the way. I don't want to like look at the first example, second example, third example. I want to see if I can make a general statement about this inequality. And what would you get? 2 to the n less than or equal to n plus 1 to the n. All right, just a general statement. We're looking at that. All right. Again, my initial work here, I kind of get rid of it because I was convinced it's working out in the beginning. I don't need to look at that anymore. I really need to look at a general statement, though. I look at the general statement, and I'm kind of curious about it. You know, when is it true? So let me just write that down. I want to start thinking now. So 2 to the n, and I'm making a general statement now, n plus 1 to the n. And I want to make sure that you understand that we're really looking for some generalized statement. So really what I'm looking for to do is I'm looking to make the n plus 1 bigger than the 2 right now. And let me just start out in the beginning. If you could say, like, if n were 1. Well, if n were 1, what would you get? You'd get 2. Well, that certainly works. Let's try n equals 2. Let me get my eraser out. I'm going to get rid of this. And what do you get over there if n is 2? Again, this checked out beautifully. You would get 2 squared. And then you get 3 squared. I hope you realize that's true too. And again, we're just trying to, you know, maybe just walk through in a general way. N equals 3. What do you get over there? 2 cubed. And then what do you get? 3 cubed. I hope you're realizing now that both sides would be raised to the same power. Both sides are raised to the same power. So really, what am I looking at? I'm only looking at this argument over here. All right? So you could actually boil this down to this. And when would this be true? This would be true for n 1 and above. But you can pick any finite n you want. And if you're more comfortable with picking 20, that's certainly true. When I say 20, as long as n is greater than 20, this is going to be true. But this is really true when n is greater than or equal to 1, as we knew from the beginning, all right? Now, by the way, I wrote this over here. I guess I probably should change this to n greater than 0. But it's true for all n greater than 3, certainly. But you could say it's true for all n greater than 1. You could say it's true for all n greater than 0 if you wanted to. And now what I mean with that, where we start at 1, I certainly wouldn't go to the negative territory with that, though. So I'm going to say I'm convinced of it. But then someone says, that's a lot of work. What did you really just show? I showed it compares nicely to a convergent geometric series. So what am I going to know? I know that this series converges now. I just compared it to that. And I used the comparison test and put that over here. We used the comparison test. The series is convergent, all right? Now, by the way, I may have some idea what the sum is, but I really don't know what the sum is, all right? I know it compares with the geometric, though. You know, roughly speaking, looking at it, I know the geometric converges to a number. This is also going to converge to a number, all right? But again, I may not know what the number is at this point, all right? So let's say, you know, for what values of k is the infinite series? And it's not easy, because I want to say, well, what are the k's? But I'll be honest with you, I think this relates to a p-series, all right? Now, someone says, I don't remember p-series. Let me go back over that. And you're going to have to do this when you study. And what's nice about having a PDF, you just can go back over it and look. You can even bookmark it if you want. And p-series right over here, all right? So I'm gonna you know, just summarize that for you, that this thing over here, n equals 1 to infinity, n to the minus p, And this thing's only can converge for this over here. All right, that's the only way it converges. All right, let's go back over here. And I'll write that down again for you. So let's put this over here. So n to the minus p, n equals 1 to infinity. And this is going to converge. Well, let me write down what this looks like. It would look like 1 plus, I can write this a little differently, by the way. That would be 2 now, right? 2 to the p plus 1 over 3 to the p plus yada, yada, yada. All right? Let me just go back over here. I want to point out you're going to have to go back in your notes a lot, and there's nothing wrong with that. And I got to go back to the p series. Over here. All right? You're looking at that. And again, you certainly want to read what Wells does too. I mean, you know, it's not that one way to do things. But it really boiled down to something pretty simple. P series. P's got to be greater than 1, right? Sorry about that. I know a lot of it makes me dizzy sometimes too. Well, this could only converge if the p is greater than 1. So I'm looking at this thing. I'm wondering, do I have what they have? And I do. So what do I know? I know that this is going to converge for k greater than 1. All right? So I know that. How do I know that? Well, I'm looking at p series. Let's take a look at this over here. You know, and I'll read it to you, and we want you to read as well. This is a positive term series. Yep, that's nice to know. You know, test for divergence. Yeah, it might be a dead end for us, but we know about that as well. Yeah, they do a comparison harmonic, do a lot of work over here. And, you know, they kind of boil it down to. I know they did a lot more work than I did. There's nothing wrong with that, though. And they say, you know, cases over here. Let's see if they wrote that down. I got to check it out myself over here, by the way. Let me read it through, all right? Positive term series, divergence test. It is conclusive when k is less than divergence, so when k is greater than k is equal to 1 series, shown to diverge. Yeah, we know it's k. Again, I said it has to be greater than 1. I did say that. We need to consider these cases over here. We are considering these cases over here. The k between that. Yeah, they got it right over here. Yep, they got it written down. Boy, they took a long time to get that. All right, long time to get that. All right, consider fast nicely. Yeah, they did it. They did it a little kind of long-winded way, though, I'll tell you. By the way, I'm the one who did that. Sometimes I do that. Sometimes I see something simple. Sometimes I see something more complicated. All right, this one, I'll be honest with you, it could be really tough to do. But I'm looking at it, and I'm thinking to myself maybe I could actually write this one down as a summation symbol. And I'll put this over here. Now, I always say this is probably a good idea to do if you can. And what do I notice? I know there's a 1 on top. And then if you look at the bottom, and I got to be honest with you, look at the bottom. I'm going to say it looks like n if n starts at 1 and goes off to infinity. I want to put what I mean by that. I'm seeing 1, 2, 3. Now, what's the next factor? 2, 3, 4. So I'm going to say it looks like n plus 1. All right? So I kind of know what the nth term looks like. And I'll write this down for you. an looks like 1 over n plus 1. And what I'm going to do is I'm going to split it actually into 2 terms, but it could be very unproductive. And someone says, why do you think it's unproductive? I'm not saying it is unproductive. I said it could be unproductive. So let me write this over here. And I'm going to write down 1 over n plus 1 can be written as I have no idea over n plus I have no idea over n plus 1. Now, why am I saying that? It looks like there's a fraction common down to n plus 1. I'm going to multiply both sides by the LCD. You would get 1 equals a, n plus 1 plus b times n. And I'm going to say n is 0. By the way, don't worry about, I'm not looking at the original problem. I know the n can't be 0 in the original problem. I'm just trying to figure out what a is. So what do you get over here? If n is 0, you get 1 equals a, because the b would disappear. Whatever I say, though, I am going to check it out. So I'm going to say the a is 1 now. All right, let me write the 1 down for you. Now, I want to see if I get the b. So I'm going to say n equals minus 1. Now, I want to point out, that can't be the case for that fraction, but I'm not looking at the fraction anymore. I'm just looking at a really simple statement. And I want to put down minus 1. What do you get? 1. Well, the a would disappear because minus 1 plus 1 is 0, and 0 times a is 0. And you get minus b. What's the b? The b would have to be minus 1. So I'm going to get my eraser out. I can write that down. Now, someone says, is that going to help me? I'm not saying it is. I'm just saying I can split it into 2 terms. Right, I'm going to write that down now for you. The sum, n equals 1 to infinity. And again, I looked at this. I got it into 2 different fractions now. So it's 1 over n minus 1 over n plus 1. By the way, this is very easy to check, and you may want to check it. You'd get n plus 1 minus n, which is 1. It works out beautifully, all right? So what I want to do is, this is an infinite sum, but infinite sums are a nightmare to deal with. And I got to be honest with you, looking at it, the first guy, if I just took him separately, I'll point out what I mean by this. If you just discover this guy definitely diverges, it's harmonic, and this guy's also harmonic. All right. Now I realize what some students want to say. They want to say, well, if they look roughly equal, if you subtract them, it looks like they'd be roughly 0. I don't want to go there. Infinite sums behave really strangely. So what I'm going to do is I'm going to start to erase my chicken scratch over here. I don't need it anymore. I don't need that anymore. I don't need this either. And what I want to do is I want to write down a partial sum. All right, so what do you mean a partial sum? I'll write this down for you. This is too tough for me to think. It's too tough. So I'm going to look for a partial sum. And I'll write this down for you. N equals 1, and I'm going to stop at n. And that's going to be 1 over little n minus 1 over n plus 1. And I'm going to start writing them down. And I'm going to do it in such a way that I'm hoping you see something when I write it down. I always say if you can write a few terms down and you get a generalized pattern, maybe you could follow it forward. So what's the first term going to be? Well, I'm starting with n equals 1. So it's 1 over 1 minus 1 over 2. I did that. Plus, now we're going to go to 2. 1 over 2 minus 1 over 3. Plus 1 over 3 minus 1 over 4. Now I got to be honest with you, this is going to be a dot, dot, dot to the very end. I'm hoping as you get to the end, though, you know we're stopping at the big N. So what do you get over here? 1 over the big N minus 1 over the big N plus 1. Well, I'm going to point out something that I think is obvious. If I looked at these pairwise, what do I notice? This thing would cancel this thing. This thing would cancel this thing. And by the way, I hope you know there's minus 1/4 here, but the very next term would have minus 1/4 in it. And I want to go backwards from this. And if you did that backwards from this, what would you get? 1 over n minus 1 minus 1 over n. I hope you start to realize we're going to see cancellations here too. So what would you get in that partial sum? Let me write that down. You would get 1 over 1. That's the first term. Everything else disappears. I mean, everything else disappears except for something. What doesn't disappear? Minus 1 over n plus 1. This is the partial sum. I'm going to call it S big N. What am I going to do now? I'm going to let that big N go towards infinity. So I'm going to write this down. The limit as the big N goes towards infinity of Sn would be identical to the limit as big N goes to infinity of this thing over here, which is 1 minus 1 over n plus 1. And that infinite sum looks like this guy over here. Just like it. Do I know the limit? I do. And the limit's 1. This is a very simple limit, by the way. What do I mean by that? When n gets really large, 1 over a really large number gets really small quick. So it's 1 minus 0, which is 1. All right, let's look at the work. Do kind of the same thing. Slightly different notation, but really the same thing. I'm using a big N, they're using a little n. Why they do that? I don't know why they did that. I guess because they were using J when I used N. That's why I had to do the big N. All right, let's look at this one over here. And again, I'm looking at it, and someone says, I guess you could do the same thing, but I got bigger problem on my hand over here. And I'm gonna tell you what it is. It's not so much the bottom; it's that top part. All right, so I'm gonna still try to write a sum down for you. And the sum you write down is going to look like this over here. And what do I notice? I notice it looks like I'm going to write down as, J now. J equals 1 to infinity. Where the top is going to be, it looks like J squared. Let me see if that's true. You get 1 squared, 2 squared. Yeah, it looks good. Now let's look at the bottom. Bottom looks like, I don't know, it looks tough, though. I'll just do one thing at a time, chase one route at a time, so to speak. So I'm going to do this first factor on the bottom. And what do I notice about it? It's like 1, 3, 5. I'm going to say it looks like it's going up by 2, all right? But remember, I'm starting at 1. So let's see. Whatever I write down, I'm going to check it. I'm going to say it looks like 2J minus 1. Let me see if that's true, if I'm getting it. If J is 1, you get 2 minus 1, which is 1. That worked. If J is 2, you get 4 minus 1, which is 3. That works. If J is 3, what would you get? 6 minus 1 is 5. Worked out beautifully. Now let's look at the next factor. And the next factor is going to be this 2, 4, 6. Boy, that looks like an even number, doesn't it? So let's write that down. I'm going to say it looks like 2J. Again, don't be intimidated. Let's see if it works. If J is 1, you get 2. If J is 2, you get 4. If J is 3, you get 6. So at least I got something. I can write the nth term down now. What's the nth term going to be? Well, an is going to be equal to n squared. This is the nth term. The bottom is going to be, I'm going to write it a little differently. I'm going to write it as 2n times 2n minus 1. Right? I hope that not too bad for you. And now I'm gonna do the test for a divergence, because I want to see, that looks kind of strange to me. I'm gonna look at the limit as n goes to infinity of the nth term. Now if it's 0, it doesn't help me. And I'm not hoping for a 0, by the way. I'm hoping for something that's not 0. So what do you get over here? On top you get n squared. And on bottom you get, let's see what you get. I noticed I made an error over here. There's an error here. That's actually 4n squared minus 2n, but let's not worry about it, all right? There's an error. I got to correct the error here. But don't worry about this. You're not going to see that error. And the reason for that is that the videos were made before I published the document. It's a prison mathematics project anyway. That's going to be 4n squared minus 2n. I think I did okay there, right? 2n. Yeah, I think I did it right. What I'm going to do here is what I think most reasonable people would do. I would divide by the highest degree variable, which is n squared. You get 1, 4, minus 2 over n. This is easier for me to analyze. I'll tell you why. The top is 1. The bottom is 4 minus 2 divided by a very large number, and that's going to shrink to 0. And what's the answer going to be? 1/4. Right now, I know the series diverges. And why is that? The terms as we go out are going to start to look like a quarter, a quarter, a quarter, a quarter, a quarter. This thing's going to blow up without bound. When you add all those quarters together, you're going to be getting to very large numbers very quickly. All right, so it diverges by the divergence test. All right. Now, granted, I have to correct the error if I can remember that, problem number 8. All right, let's go to problem number 9. And I'm looking at that, and I'm wondering, it's got that factorial notation in it, and that's really tough for me to deal with. I mean, I'm not going to, maybe I should write it down. Let's put that down. So the summation, and I'm going to use the J again. J equals something. I have no idea. But I'll write this down as looks like 1 factorial. I think I can do that. It's a fraction. It looks like there's going to be a J here. 1, 2, 3, 4. And then they look like a power. And, oh, wait a second. It's not J. The number is always going to be 2. Let's write that down. I'll write it over here. 2. Now someone says, I don't see the 2 in the first term. You could make it 2 to the 0. That's 1, right? So what do you get? I'll erase that later, by the way, because I realize when I write something over, I'm going to say, where was that? We'll get back to that later. So I'm going to say j should start at 0. All right? 2 to the j gives you, 2 to the 0. Wait a second. That's still not going to work, right? And why is that? Well, if you look at it, I'm still missing a term there. So you know what I'm going to do? I'm going to start adding it at a different level. And this is always important. You can do that. So let's get my eraser out. And I'm starting to think, maybe life doesn't always work out smoothly. So someone's going to say, where are you going to start adding from? Right from the pattern. I'm going to do this one over here, and I'll write this down for you. 1 plus a series. Let's write this down. What am I seeing over here? 2. And I'll write this down for you. I'm going to say j starts at 2. Off to infinity. All right, so let's see if we got that. 2 squared, 2 cubed, 2 worked beautifully. What goes on bottom? Well, it would be j, 2 factorial, 3. Wow, that worked beautifully too. So I got my general term. All right, I'll write it down for you. What's an? An is actually 2 to the n over n factorial. Right, now since I'm going to use the ratio test, again, you may want to go back in your notes, look what the ratio test is. It's a nice test, by the way. I'm going to write down an for you. Oh, I already did that. I'm going to write down an plus 1. What's that going to be equal to? 2 to the n plus 1 over n plus 1 factorial. Now, what I have to do, which may seem very difficult to you, I've got to write down this ratio, but I got to take the absolute value of it. Let me write this down for you. So I'm looking at the ratio an plus 1 over an. Now I'm going to write that down. Now, I'm noticing about these things, they're always going to be positive terms, by the way. So I don't have to worry about any negative numbers. So really, what is it going to be? It's going to be, it's going to be 2 to the n plus 1 over n plus 1 factorial divided by, it's easier for me to write that down, by the way, 2 to the n over n factorial. Well, I'm still going to simplify that. And what do you get? 2 to the n plus 1 over n plus 1 factorial times what? N factorial over 2 to the n. Does this reduce nicely? It does. What are you left off with? 2. All right, simple rules of exponent. And let me just go through this with you. N factorial, and the bottom is n plus 1 factorial. Well, the top is n factorial. The bottom is n plus 1 times n factorial. They cancel off. You're left off with n plus 1. A lot of work, right? A lot of work. All right, so let me see what they did over here. I wonder if I went crazy with this. And I have to look at this again. I don't know what they did. You know what? I have something different here. This is not the problem. Not the problem. I guess I wrote something down different. I really did. And this is not the problem. All right? I must have been doing something else and copied it. So this really needs to be corrected. You're not going to see that, though. The work that I'm doing is correct work. All right? So I'm looking at this over here, looking at the limit. What's the limit of this guy over here? It's pretty simple, actually. Let's write it down for you. Limit as n goes to infinity of 2 over n plus 1, which is 0, and this is clearly less than 1. This series converges, all right? It converges. I got to correct that too, by the way. Sorry about that. All right, this one over here, you know what? I think I copied the wrong problem here because I noticed 9 and 10. Nah, maybe not. Maybe not. I'm not sure where that problem came from, by the way. I have to look into it. I make mistakes all the time, by the way. But the work I put down is for the problem that's listed, right? The blue work, not the same problem. It's not the same problem, All right, and I apologize for that. It happens sometimes when you type up. You could imagine a document that this long, there's got to be some error somewhere. I just caught an error. All right, this one over here, let me look at it. It looks pretty simple. I'm going to kind of speed it up a little bit. Let me see what time I got here. Yeah, I got to get moving quick. Got a meeting. But anyway, you know what I'm doing over here? I'm writing down the nth term. I'll write that down for you. That's the nth term. I'm using the ratio test. I write it down this way over here. And the reason that it's easier for me to do that, and this is a positive term series, so the absolute value has no value in it. I wrote this over here, Let me see if I reduced it right. Let's see, that would be 2n. Yep, n plus 1 cancels off. Yep, that looks good. And then I took the limit, and the limit of that would be 2. 2 is greater than 1. What do I know about this series? It definitely diverges. All right, this one over here. Again, I know I'm cutting it close to the edge of time over here. I realize that. There's a lot of problems here. I know that. This is an infinite series. And I'm going to say, looking at it, just looking at it, it really does look harmonic. All right, it looks harmonic. But anyway, I wrote this over here. That's the general pattern for the nth term. I did a comparison test. And I'm comparing it actually to the, I should say I'm doing a limit comparison test. I'm comparing it to the harmonic. We know the harmonic is divergent. And I put this down over here. I get this number, series diverges by the comparison test. Or I'm going to say the other one's really not that bad to do. I realize I'm speeding through that. I do have to get to a meeting, and that's why I'm doing that. 13, I did the ratio test on it. 14, I did the ratio test on it. 15, ratio test probably on that one too. Yep, ratio test. 16, I'd say ratio test again, and then you get the exercises. I know this is a lot of work. This is an extremely difficult section to get through. Right? I know I blew off on a few problems there. Look at it. You need me to do the work. I don't mind making other videos for you, but you want to get through the work over here. This is tough stuff, though. No doubt about it. I do want to get to the SAGE thing. Wow, they really got a lot of problems, don't they? And you can see how much work goes into those problems. All right? Related SAGE code. What's SAGE? Computer Algebra System, CAS. It's free. Go to that website. You can download it or use the interactive web-based application. And what I do is I do a bunch of problems. All right? And when I say a bunch of problems, coding it, putting it in, going, trying to evaluate sums and things like that. All right? I wonder why I'm doing, I got a sum over here. And I got log. It turned out to be a log. It's amazing. By the way, if you're looking at this symbol over here, it's two O's next to one another. It's supposed to look like an infinity, right? So what it's doing is taking a sum from 1 to infinity. That might seem remarkable that a machine can actually take a sum from 1 to infinity. Because that, no matter what anybody thinks, that should take forever. It's not actually adding term by term, by the way. It's doing something completely different, all right? But anyway, my goal here is not to get you to use SAGE. My goal here is to get you to use, sorry about that, is to get you to use what we learn in class, right? What we learn by reading, doing the problems. And granted, you know what? I just noticed that I did some errors in my work. There could be errors in this work over here too. So if you're going through these problems over here and you feel there's an error, or you say, oh my God, I have no idea where this is coming from, email me. Let me know that, all right? Let me know that. I may not be able to get back to you, but if you say you're at 84.3 and you tell me there's a problem with number 1 and what the problem is, I'll carefully look at it. I promise you that. Thank you.